Okay, so the second half of our unit, like I said yesterday, really focuses mostly on theory questions. Yes, there is a little bit of math. There's two formulas, one which we're going to talk about today. But for the most part, this is all about just knowing properties and types and knowing kind of how waves work. So a quick recap of yesterday. Yesterday, I think I have maybe two main goals. First goal, I need you to know all the different definitions and terminologies associated with a wave. So I'm going to do a quick recap of that. If I ask you what an amplitude is, what does that mean? Yeah, the height of the wave, basically, right? What does amplitude mean in real life? If you have more amplitude, you have more. That'll work, more diameter or radius. It could also mean you have more energy. Maybe it's a louder wave, right? Basically, the higher the wave, the stronger it is. Whatever the context it happens to be, right? If this is a pendulum going back and forth, it's just going back and forth further. Right? If it's a car tire going around, then like you said, it would have a higher radius to the tire. If it was a sound wave, the larger the amplitude, the louder it is. Does that make sense? What is a node? Sure. And another good way of putting it is think of it as an x-intercept. Right? I mean, when the pendulum goes back and forth, when it's right in the middle, that's a node, essentially, right? Antinodes are known as either the crest or a trough or trough. Do you guys actually know? What's the correct pronunciation for that? Do you know? Trough, I don't know. Trough. Anyways, high part and low part. Let's just go with that. I don't care how you say it. Long story short, those are your antinodes. Those are when it's at its maximum displacement, right? That's another term you should know. Frequency would be how often the wave seems to repeat itself in a second. Period would be how long it takes. And period is really related to wavelength. We've got a formula we'll learn today. I'll use this wave right here. If I ask you to find the distance from here to here, this distance could either be measured in meters, which is a wavelength, and wavelength is using the Greek symbol lambda. So basically it's a distance from this point to this point. Or it could get measured in period, which could be in seconds. Both are considered kind of a valid way of doing things. So it could be the length of time it takes this point to get to this point, or it could be the distance between this point and this point. That's a wavelength or a period. I can't think of any other. Oh no, there's a few more we can use. Do you guys know what like a wave? Is it a wave front is? Something would be used. Yeah, this is it. Wave front. Right, the idea that sometimes we can't draw this in 2 dimensions because it's really more of a 3-dimensional. So think of this as being a top-down diagram. The source of whatever is the wave, the peaks are at the wherever the lines happen to be. So you have to think of this as like a wave that's emanating outwards, but it emanates outwards in all directions, right? In 3 dimensions. So that's why I had a couple of pictures here to try to illustrate that point. The last thing I wanted you to get yesterday, you should know how to roughly make an equation. And the rough idea of an equation is the leading coefficient is your amplitude. And you have to take 360 because that's how many degrees are in a circle, if we work in degrees, and divide by whatever your period or your wavelength is. If we ever work in radians, which we probably won't, I don't see any reason why I'm going to throw that at you yet, but you can in math when we do radians in like 30-1 and 20-1. Rather than using 360, we'd use 2 pi instead. Because 360 and 2 pi have an equivalency. Anyways, that was kind of the lesson from yesterday. That so far so good? Today, I guess I could say that I also have 2 main outcomes. I want to introduce to you 2 more terminologies and 1 formula. So I'll start off with this slide here. There's actually 2 types of waves. Further to what we've talked about. I mean, we've already talked about the properties of waves. There's the 2 types. There's transverse and longitudinal. And I have the spring along the floor to help illustrate it. Sorry that you guys won't be able to see this all that well, but I'll try to explain what's happening. Here's one type of wave. As I have the spring sitting here, if I have a pulse that goes off to the side, right? Hopefully you can see that kind of has a wave shape to it. It's not perfect because there's too much friction and the spring's kind of bent, right? But what we have here is on this side and right this side, we have our, our top and bottom. There's an amplitude of however tall it is, right? This is a transverse wave. Fair enough? The other one is a longitudinal wave. If I do this, it's not really supposed to have a, it's kind of like coming up like that. It's not supposed to do that. So if I just give it a pulse, then I can do a better job here. Pulse. That worked better. You see how that kind of went to the string there? You can see how the pulse is resonating through there. Obviously, there's too much friction on this floor for it to actually make it all the way to the end. But that's another type of wave. Pulse, 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 pulse. The distance between the pulses then would either be your period or your wavelength. Okay, so amplitude doesn't necessarily apply nearly as much to something like that. So hopefully you guys can kind of see that in the pictures I have here. Transverse is the typical sine wave that goes up and down and up and down. A longitudinal wave is more like a pulse. Okay. Here's how I remember them, and you guys can use your own method. You guys know how there's like latitude and longitude on Earth? Latitude is like this way, and longitude is this way. And I like this picture here to help me describe it. I need to get the pen thing right here. I like this moving diagram here. This right here, it's going up and down, right? Kind of like we're expecting it to. So this is your transverse wave. This one here, you see how like you can see these pulses that are just moving side by side by side in a way that's kind of like lines of longitude on the Earth. You guys know latitude and longitude? Okay, so in a way, this pulse, this is a very slow moving pulse, by the way, right? But this is a pulse, this is a second pulse, this is a third pulse, this is a fourth pulse. Right? They look like longitude on the map. So transverse, longitudinal. Okay. They both have very similar properties, right? In a way, what you need to try to calculate is from, say, this max point right here until this max point right here until this max point right there, right? The distance between that would be your period or your wavelength. Right? Same thing right here. The distance from here to there, it's moving on me obviously, but that distance is essentially your amplitude would be in this direction. That's your amplitude. For this one right here, amplitude is actually best measured from like where the middle would be. So the lowest it gets to is about there. The highest it gets to is about here. So that's your amplitude right there. Properties for this graph are a little bit trickier, just because it doesn't really visualize in the same way. This is more of a pulse. Sound waves are actually a good example of longitudinal waves. When I'm speaking, and I've got some pictures on the next slides here, it actually isn't going up and down and up and down and up and down in that same way. It's more just emanating outwards as a pulse, and your ears pick up that pulse. So here's something I need you guys to know. I will give this to you on tests. But sound is about 330 meters per second. That's actually an important value to know. Okay. On a test, I should give you that number. Okay. But just so you're aware, on any test questions, if it feels like you're missing information, that's the speed of sound. Roughly, because it actually depends on temperature, altitude. Have we used the word medium already in this course? Okay, so medium's when it travels through. I don't need you to memorize these ones, but stuff travels at a different speed through different stuff. So sound actually travels faster in water, and even faster in iron, which is kind of crazy. Not that you usually transfer sound through iron, obviously, but different mediums transfer sound differently. I think part of the reason why is that water and iron, when you think of their molecular structure, are much tightly packed together, and so when one molecule vibrates the next one, which vibrates the next one, that's a lot easier to happen in a solid because all the molecules are literally right next to each other. Whereas as you're having molecules vibrate in air, they're loosely compacted, right? Like this molecule here and there and everywhere. And so it takes a while for them to crash into each other, way less so than iron when they're right next to each other. Here's a picture of basically what, if we could see, what a sound wave would look like. Right? You have a speaker. The speaker is putting out some noise. I mean, maybe you can envision like the subwoofer is boom, 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 right? You can actually see it moving, right? As it vibrates, it sends out a pulse, and that pulse is going to be a compression on certain sections, right? Just like this diagram was right here, we can see where the compressions are. Right? And so as it emanates outwards, the distance from here to here is the wavelength. That wavelength can then help you figure out a frequency, and a frequency will then tell you what pitch you're hearing. So the second half of my lesson here is to try to tell you how to convert from wavelength into a frequency, because there's a formula for this. Before I get to that formula, though, a little bit more on waves. This is the other type here. Transverse waves. Light would be a good example of that. And anything on the, do you guys know the electromagnetic spectrum? We've heard that phrase before. I believe it's in like the grade 7 or 8 curriculum. So maybe it's been a while. But like you're talking about things like radio waves, they're very long range waves. Microwaves are actually a little bit shorter. Then there's the infrared spectrum. Then there's visible light, so it goes from red, orange, yellow, green, blue, indigo, violet, like the Roy G. Biv acronym. You said that before? Red, orange, yellow, green, Roy G. Biv, indigo, violet. You've heard that. You guys heard that one before? Okay, I'll move on. And then all of a sudden, then you get into the really short ones. These are the ones that are more dangerous, by the way. Like X-rays. Obviously, like if you've been to the dentist or you go to, I don't know, you get some sort of medical procedure done, right? Often they put like a lead vest on top of you because too much X-ray exposure can cause some issues with reproductive organs for sure, your liver probably. Ultraviolet rays. What's the problem with ultraviolet rays? You guys know? Yeah, it's going to cause skin cancer, right? Well, what do we use to try to prevent UV radiation? Sunscreen. That's what I was thinking. Yeah, sunscreen. Right. That's why when it's particularly there's a high UV index outside, you want to have sunscreen on because these rays can damage you, right? And I mean, gamma radiation. I mean, not that it's just fan fiction, but like in like the Marvel universe, the Hulk comes from gamma radiation. That's far-fetched, obviously, but I mean, gamma radiation is very intense, very short-range stuff. It can penetrate through the human body and cause some pretty big issues. So, usually, the idea is that the shorter the wavelength, the more dangerous it is. Just so you guys know, things like our cell phones kind of fall into this sort of range right here, the frequency that your cell phone uses. So it's actually very, for the most part, we don't actually have any evidence that it's harmful because the waves are so long that they really can't hurt. If the wavelengths get really short, they can actually penetrate through the human body, which is why X-rays can penetrate through the human body but not through bones. They get stopped by bones. That's why you're able to see them. You know, that's why they do the X-rays. Anyway, moving on. Here's another picture of the same sort of thing here. In terms of frequency, gamma rays, X-rays, UV, they have the highest. I don't want to spend a lot of time on this because we have an entire unit actually in Physics 30 on the electromagnetic spectrum, but you guys seem to have heard of this before. So, okay, moving on. Here's another number I need you guys to know. Light travels at 3 times 10 to the 8 meters per second. That is its speed. Officially, we've actually discovered it to be 299,792,458, but we're not going to use that number. That's kind of insane. It's on your data sheet, by the way. You guys know where there's that section where it talks about like all the constants? It often gets represented by the constant c. You've probably heard of Einstein's formula, E equals mc squared. The c in E equals mc squared stands for the speed of light. So if you ever need to look at the speed of light, this is on your data sheet. So I need you guys to know for various questions the speed of sound in air and the speed of light. Okay, so one of them is about 330 meters per second. The other one is 3 times 10 to the 8 meters per second. And we'll need those in our equation, which is next. So there's the first half of my lesson. No transverse and longitudinal waves, and just the basic properties of them. The second half of it is there's a little bit of math we can do on them. We need a way to relate the speed of the wave to the frequency or the wavelength that's associated with that particular wave. So here's how this works. You guys know how speed is normally velocity is distance over time? Well, the distance that a wave travels, if I were to kind of sketch out a wave, I mean, the wave is obviously continuing on and on until it bumps into something or interferes or stops, but you can consider like from here to here, so from there to there, to be a distance. Only we have a different name for that. Rather than calling this a distance right here, we call that a wavelength. And rather than this being a time, the time that it takes for it to go from here to here is known as a period. So one formula could be a velocity would be a wavelength over a period. Basically, it would be a meter per second. However, traditionally, for whatever reason, I don't actually know the reason, traditionally we write the formula a little differently than wavelength over period. We write it as wavelength times frequency. And the reason why is that, remember how period to the -1 is a frequency, like the reciprocal is there? So if you have period on the bottom of a fraction, to just avoid fractions in general, you can then just put a frequency in its place. Now there's no fraction to deal with. So this is one of the most important equations that we're going to use going forward, not just in this unit, but throughout most of Physics 30 as well. It's known as the universal wave equation. I would suggest that it's a pretty common thing for kids to ask me, Chris, I don't think I have enough information. And most of the time, not most of the time, but a good chunk of time, it's because they haven't considered this. If it feels like you're missing information, use this formula. The reason why you can use this formula is that the velocity is implied. If it's light, you now know the velocity of light, 3 times 10 to the 8. If it's sound, you now know the value of it is 330 meters per second. Does that make sense? So if it feels like you're missing a piece of information, there's a good chance you can use the universal wave equation to either turn a wavelength into a frequency or a frequency back into a wavelength. So make sure we're clear on what these mean again. A frequency is how often the wave zips up and down in a second. So it might oscillate 100 times in a second. It's a very fast frequency. When I was pulsating that thing there, I was probably pulsating it like once per second, or a low frequency. Whereas wavelength is the distance between as it goes up and down. So let's try some examples. These ones are pretty easy to pick out when you have to use these ones because you only get one number. Like I gave you a cordless phone. Your cordless phone operates on a frequency of 900 megahertz. If it feels like you're lacking information, it's because it's kind of implied what the other number is. Now, this isn't light, but anything in the electromagnetic spectrum travels the speed of light, just so you guys are aware. So anything, you guys remember that slide I had way back here where you have all your different types of waves? Maybe this one's better here, where you've got your microwaves, your radio waves, your visible light, your gamma rays. All of these travel at a velocity of 3 times 10 to the 8 meters per second. Does that make sense? So it doesn't even have to be light. It can be your cell phone signal. That's traveling the speed of light as well. So in terms of information you have, you know your frequency is 900 megahertz. I'm going to make one little twist here though. Rather than writing megahertz, I'm going to call it 900 times 10 to the 6 hertz. You guys pick out how I managed to do that? I just changed the mega to a 10 to the 6. We know the velocity. The velocity is 3 times 10 to the 8 meters per second. We have the information we need. So velocity is equal to frequency times your wavelength, f times lambda. Your velocity was 3 times 10 to the 8. Your frequency was, can I call this 9 times 10 to the 8? Let's see how I pulled that off. If this is 900 to the 6, then maybe I can just call it 9 and just throw the 2 extra zeros onto there. You could write it 900 times 10 to the 6 if you want. Anyways, long story short, we just need to divide by this. So our wavelength should be 0.333 meters, because it's 3 over 9 is 1/3, right? You guys calculate that as well? So what does that mean? Well, it means that if you were to think of your cordless phone operating like a wave like this, the distance between wave crests is 0.333 meters. Is a meter stick? It's a third of a meter stick. That's how big that wave is. That's not overly dangerous. That's why we can use cell phone frequencies and radio wave frequencies, because that wave is so large, it's not going to penetrate your body. In fact, it's going to go around your body most of the times. Does that make sense? But if you had wavelengths and frequencies that were really, 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 really small, like X-rays and gamma rays, that can be dangerous because those can actually fit in between the molecules of your body. That makes sense? So if that wavelength was like 0.0000001 meters, well, now that's the size of like an atom. That can actually physically go through you. But this is too large to be really concerning. Does that make sense? All right. Let's figure out the frequency of red light. Red light has a wavelength of 700 nanometers. Okay, so right off the bat, we have a wavelength of 700 times 10 to the minus 9 meters. Or if I wanted to rearrange it, I want to make sure I don't screw this one up. I believe that would be 7 times 10 to the minus 7. You see how I did that? I took off these 2 zeros right here, but then I have to add 2 more zeros to this, but that makes the number get bigger, right? So it goes from -9 bigger by 2 zeros up to -7. So there's your wavelength. And then we know the speed of light, which is, this is literally light, so the speed is 3 times 10 to the 8 meters per second. So the wavelength for this one is way shorter. If I were to draw a picture of it, the wavelength of this is, I mean, again, if I draw this picture, the distance from here to here, rather than being a third of a meter, which is a very large wavelength for a radio wave, this is now like a nanometer. I don't even think I can put my fingers that close. It is so incredibly small. That being said, light does not pass through you though. Your body is still going to block that light, which is what creates shadows, if that makes sense. So although it is small, it's not actually small enough to phase through a human being or other matter, but it is possible to find wavelengths that can actually go through other materials. Right, anyways, to solve this one, V equals frequency times lambda. 3 times 10 to the 8 equals your frequency times 7 times 10 to the minus 7. Divide that out. I can't do this one in my head though. You guys get an answer? 3 times 10 to the 8 divided by 7 times 10 to the minus 7.
4.29 times 10 to the 14.
Anybody else get that? Okay. What would the unit be? Good. Yeah, it hertz. Or you can have it over seconds if you want to. Or you can put it as seconds to the minus 1. Or you can just go with hertz like you mentioned there. All of those would be correct. So what that means is that this is happening very frequently. Right? This wave oscillates up and down that many times in 1 second. You know how when I was waving that thing back and forth like maybe 1 time a second? If I could manage to pulsate it that fast, it would actually become light, I guess. That's how fast it would be moving. Does that make sense? Okay, one more time just to make sure we're clear on the terminology then. Frequency is how many of these things you can have fit in 1 second. And so like if from right here to here, if this was 1 second, then it looks like it's pulsated like 1.5 times. That makes sense. So that'd be your frequency. Your wavelength is the literal distance between these things. Long and short of it is, if you've got your electromagnetic spectrum, your low energy things, like your radio waves, your microwaves, you know, like old school TV signals, like over the air, we probably don't use that all that often anymore, right? But those signals are very long distances in terms of that. They're relatively harmless. But as the wavelengths get shorter and shorter and shorter, like I said, it gets so small that it can actually phase in between matter itself. Right? These ones will just go around or get blocked by it. But that's why X-rays will go through human flesh, but not bone, for example. I guess that's about it. Well, I guess one more thought here. This is amplitude. There is no formula for amplitude, though. Because what does amplitude control? Loudness, how much energy there happens to be. So if you want to make it a louder wave, if you want to make it a more powerful wave, you increase the amplitude. That makes sense? And that makes it a taller wave. But it doesn't increase its speed, it doesn't increase its frequency, it just makes it a taller wave, that's all. Is there any questions? Okay. Managed to finish in time still. Okay, you guys have a little bit of time today. Sorry it wasn't as much as normal. Tomorrow we're going to do one more lesson, and then Thursday we're going to do a lab. Use the last 20 minutes for whatever you need to.